So last time we have started proving this theorem about approximate valuation. It basically says that if you are given points P1 to PH, and points always mean DVR and valuations. So they define valuations V1 to VH respectively, and what you want to find is a U in the function field such that the valuation of U minus some offset function which is already provided to you is at least mi, an integer which is already provided. Okay, so the only unknown here is U. And the key thing is that you have to find a U that works for all these inequalities simultaneously. That's the hard part, because in the base case when H is equal to 1, let's make this bigger. So when H is equal to 1, that's the base case. So there you only have one inequality. So in that case you can pick your U to be just U1 plus the uniformizer for V1 alpha 1 to the M1, right. So you will have actually exactly valuation equal to M1. That's easy. It will work whether M1 is 0, positive or negative, right. So you will get at least valuation V1 to be exactly M1. But when you have both V1 and V2, then it's actually trickier, because now you have two uniformizers and two numbers M1, M2, and also two offsets U1, U2. So you don't know how to do a similar trick. It's not very easy. So these are the offsets. So when you have multiple offsets, then it's a problem, and multiple valuations. So first thing we showed, claim 1, is, basically the proof will be induction on H, how many inequalities you have, how many valuations you have. Assuming that you have shown it till H minus 1, you can immediately get claim 1. So what claim 1 is saying is that, assuming the theorem for H minus 1 up to H minus 1, you will always be able to find a U such that VIU is equal to given EI. Okay, so this is a simpler statement than the theorem statement. The theorem statement has an offset because it's a stronger result. The stronger result will give us the weaker result, which is claim 1. Okay, it's defined in a way so that you get claim 1 by induction. The proof of this is very simple. You first find Wi such that Vi Wi is equal to EI. Okay, so this is not a common thing. You do it for every EI, and then you apply the theorem. So now you use Wi as the offset and find a U such that Vi U minus Wi is at least EI plus 1. So by the theorem statement for H minus 1, you will get that the valuation of U is exactly EI. Is that clear? So on the given points and the valuations, which you can also think of as multiplicity, that's why we call it M. Okay, so for given points PI's and given multiplicities EI's, what claim 1 is saying is that you can find a U such that that point's multiplicity is exactly EI. Okay, that's the key thing you want to prove about functions versus points on the curve. Yeah, but we haven't shown, now we have to show the induction step, right. So you want to get to H now from H minus 1. So for that we'll need to show that, we'll actually do many things, but first thing we did is claim 2 showing that the valuations are always independent. Suppose not, so we have this, for the sake of contradiction, we have this dependence VH on every u is equal to a linear combination of VIU for the same RIs. Okay, suppose there are rational numbers RI such that VH is as a valuation function, it's a linear combination given by RIs of VIs. So it's true for every u in the function field. And then we showed that there are contradictions in every case. I will not repeat that proof. Any questions till now? At some point I will post this, but you can also see the proof in the old lecture notes. So okay, so now what we have to do is the inductions, we have to complete the induction step. So our plan now is that we will construct this U, which is a combination of the offsets UIs. We will find these Xi's, okay, such that we will in fact design these Xi's in such a way that the U which is sigma Xi UI will work. It will give you the theorem statement. So U minus the offset valuation is equal to this thing. So we will basically design Xi's so that X1 minus 1 and Xi valuations are under control. So let's move in that direction. Oh, I need another claim which follows from claim 2. So I want to show that there exist functions z1 to zh in the function field such that the determinant of the matrix Vizj is non-zero. It's an invertible matrix. Okay, so this is an H cross H matrix. It's a square matrix, and we are saying that it's an invertible matrix. There exist such value functions whose valuations have this define this invertible matrix. This actually is an easy consequence of claim 2. It again is an evidence of VI's being independent. But how do you find these Z1 to ZH? So kind of an inductive proof. So suppose you want to find Z1. So let's look at an equation. The solution set of sigma Ri Vi Z1 equal to 0. So consider this solution set, it's a vector space, of course. Now what I want, I don't know what Z1 is, what I want is that a Z1 such that the rank of this solution set is 1 less. Okay, I want to claim that such a Z1 exists. This is because VI's are independent. Do you see this? See, for all the Z1s in the function field, the rank of this is always maximal, which is H. What would happen? This should just be linear algebra. I think you should think of Vi, the function, as a vector evaluated on all possible Z1s. Okay, think of it as an infinite vector. And you have shown that these vectors V1, V2 dot dot Vh they are linearly independent, right? So it basically means that there has to be a Z1 at which this rank is smaller than expected. It's smaller than the maximum, which is H. Do you see this? So just prove this by linear algebra. And claim 2, we have shown claim 2. That was the important thing. Okay, next what we will do is, so this only gives us Z1, we also want now Z2. So we look at two constraints. So consider the vector space of the solution set of this and some other Z2. And the claim is that this is equal to H minus 2. This is equal to H minus 2 for some Z2 in K star. Now the first constraint already reduces the dimension by 1. So you are in R bar cannot be more than H minus 1 dimensional solution set. The second constraint, so Z2, think of it as unknown, Z1 is fixed. What you do is that from the first constraint, you say you you express R1 or RH as a combination of R1 to RH minus 1 and plug that in the second equation. Right. So second equation is a linear constraint in R bar, but now one less. So you only have R1 to RH minus 1. So you rearrange and you basically do what you did in the orange part, that there will be a Z2 because of the linear independence of V1 to VH minus 1. V1 to VH. Because of the linear independence of that, there will be a Z2 such that the dimension is 1 less than the number of R's, which is H minus 1 minus 1. Is that clear? So plug the first in the second. So when you plug it in, then you basically instead of R1 to RH, you are looking at only R1 to RH minus 1. And by the first orange conclusion, you will now have H minus 2 for the solution set. Yeah, so we have found Z1, we have found Z2, and then we can just continue this and we can find.
What do you mean plug the first?
Oh, the first one, Vi, Z1 are just known numbers, right? So suppose you have an equation, this is giving you the equation R1 plus R2 plus R3 equal to 0. So you write R3 as minus R1 minus R2 and just substitute that in the second equation. So R3 is eliminated. So now actually you are only looking at H minus 1 Ri's, and since this Vi, Z2 are unknown, valuations which you know are linearly independent, you'll find a Z2 so that the solution set is smaller of R bar. So it's again coming from claim 2. And yeah, so when you keep doing this, so on repeating this, we get that we get Z1 to ZH in K star such that no non-zero Q linear combination of so VIZJ. Vanishes simultaneously Okay, so you look at these vectors v1 to vh evaluated at zj for all j. So you have these h vectors. You have what you have shown is that there is no single vector which is orthogonal to all of them, right? Because the first one had already reduced the dimension to h minus 1. Second one will make it h minus 2. When by the time you reach h, you would have h minus h. So the only vector which is simultaneously orthogonal to all these is the 0 vector, nothing else. Which is another way of saying that this matrix is invertible. Right, which is the same as saying the determinant is non-zero. Is that clear? Yeah, I don't think I needed to do all this. I could have also said in the beginning that just because VI's are linearly independent functions, you should be able to find Z1 to ZH. For example, if you just picked in a sense randomly from the function field, you will actually satisfy this determinant being non-zero condition. But I guess you get some idea of the proof also. Key thing is basically looking at these VI's as these infinite factors evaluated at all possible z's, and you are given that these infinite factors, each of them are linearly independent. So you should be able to basically find a minor h cross h which is also invertible. This is what the proof is doing. Okay, so how does this claim help in the induction step? So once you have this invertible matrix, you solve for that is, you want to find u. That would be the goal now. And for u, we will find xi's explicitly. So let's solve for the following equation. Solve for c's such that sigma cjm times VIZJ is equal to -1 if I is m and 1 otherwise. It's basically, so think of C as a matrix, right? It has entries j comma m. We will be doing this for all m. Think of this as h cross h matrix. I think it's basically the matrix which when you multiply with this Vi Zj matrix, the product is 1 everywhere except in the diagonal you have -1. Is that right? Yeah, I'm doing this for all IM. So in the matrix product, if you look at the m comma or I comma mth entry, the I comma mth entry is this linear form, and this value is -1 only in the diagonal when I is m, otherwise it's 1. Okay, so this is a simple C comma V matrix equal to all 1 except in the diagonal that is happening. So this matrix times the C matrix is equal to -1, and everywhere else we have 1. Right, I hope this these subscripts are not messed up. Yeah, so I comma mth entry of this product matrix is what the constraints I have written. So anyways, this C is easy to find because V is invertible. So C is just equal to V inverse times this matrix. So it exists because V is an invertible matrix, we just showed. Okay, and so C's are, yeah, in general they will be rational numbers. So we convert them into integer. Are integers. Okay, basically look at the denominator that you get in the solution matrix and multiply by the LCM. D is the LCM. So these will become, the matrix C will become an integral matrix now. And now we have a sequence of mysterious designs. So first design is define Ym to be product of Zj d Cjm yeah, so we want to take a product of the Zj's that we had found, raising it to these exponents which are now integers that we just found. So where is this? This is happening in the function field, right? So Ym is now a function. So we have designed these H functions from Zj, and let's record its valuation. So what is the valuation of Ym? Vi Ym. So by this orange property which we wrote, you should be able to deduce that valuation of Ym is, there was a -1, right? That -1 will become -d, and +1 will become +d if I is equal to m, otherwise. Fine, this is the point of this design. So we have found these y1 to yh such that when they look at their valuations v1 to vh, they are a sequence of minus d and plus d. Is that clear? And finally, another mysterious design of a rational function, which is xm, which will be 1 plus ym inverse whole inverse. Okay, so these will be my xm's, which will define the u that the theorem wanted. So let's check the valuation. So valuation of xm is what? So when I is different from m, what happens? Vi is, you are taking, this will be equal to minus Vi 1 plus ym inverse. And what is the valuation of 1 plus ym inverse? So valuation of Vi1 is 0, Vi ym inverse is what? This is minus d, right? So 0 comma minus d. So the answer will be minus d, which is d. Fine. So valuation Vi of xm is d, and the other thing I have to see is xm minus 1. So what is that? Sorry, Vm of xm minus 1. So Vm of xm minus 1 is do you have any handle on that? So xm minus 1 will be this, right? Which is what do you know about this? So valuation of ym plus 1, so valuation of ym is minus d, and Vm1 is of course 0. So this valuation is minus d and invert it, so d. This is again d. Okay, so we have checked that for this design of rational functions, Vi value is d for I different from m, and Vm of xm minus 1 is also d. Okay, so let us now move to the design of u for the theorem. So u will be sigma xi ui, the offsets. And you have to check the valuations now. So u minus ui is equal to m in each and m not equal to I. So yeah, let's check Vi of u minus ui. That is what you want in the theorem statement, right? You want to evaluate the valuation of ith valuation of u minus ui. So this will be, what will you get from here? So let's check vi of well, vi of xi minus 1 we have evaluated already. So that is d or d plus yeah vi ui, and this part vi of xm vi of xm um. Okay. Yeah, but I want the valuation of the sum. Can I control that? Okay, so yeah, so the thing is, what you want here is that this should be greater than equal to mi, right? This is what you want to show in the for the theorem statement. And here in the valuation of the summands, you see that you are getting these two numbers. But d for now is free, right? So you can just pick d to be large enough so that these two values they exceed or they at least are mi. So let us just remember that in the design. For fix d large enough such that d plus vi uj is greater than equal to the max of mi's for all ij. Is this fine? So if I pick d to be a big enough number, then well, actually kind of we had already fixed d. We also had this, we had said that pick a d such that d times cjm is are integers, but there are many such possibilities for d. So you keep on increasing d such that all these constraints are satisfied. That's easily done, and then now you can deduce that vi of u minus ui, since both the summands it's at least mi, valuation is at least mi, so your theorem statement is done. Is that clear? So this completes the induction step. Gives you the theorem. Okay, so we constructed ultimately u as a combination of the offsets. And these xi's, how are they constructed? So they are basically, I mean, if you want to reverse engineer the proof, you should look at this expression u minus ui, and from this you can see why we designed these mysterious looking rational functions ymxm. Okay, and one more thing we should remember from this proof because the whole the subsequent part of the course is really an attempt to understand this corollary, okay, or investigate this corollary, which is that the thing that we showed here in the very beginning, I think claim 1. Yeah, claim 1 that given multiplicities and points, you can always find a function which has those valuations. Okay, let us just remember that as a corollary of this theorem. So S is a subset of S is a finite subset of the smooth projective curve C. And you are given multiplicities, candidate multiplicities. So these are of course integers. So you are allowed to specify P as a 0 or as a pole. Okay, and you can also give multiplicities 0 of multiplicity 1 or 2 or pole of multiplicity 100, so minus 100. Then there always exists a rational function f. So K, remember, is this function field of the smooth projective curve. Yep. Such that these multiplicities are matched. Okay. So this is a very important result. In fact, this is the most important result you have seen till now in these 2 months. Okay, and this important result is what we will now kind of go really deep into in the next 2 months. So you have some your favorite finitely many points P's and multiplicities, and you want to study these functions. So we are obviously not saying that there is a unique function, right? There are infinitely many f, because any f you can multiply by constants. Constants are infinitely many. So obviously you have infinitely many functions which will have these zeros and poles with this multiplicity. But now we will be interested in measuring how many. Okay, they are infinitely many, but you can actually show that the set of these functions kind of form a vector space over the base field, and you are interested in computing the dimension of that vector space. Okay, that will be the goal, and we will do a lot of stuff in this basic question following Riemann. So any questions till now? Or maybe I should have discussed this question over the affine line. So when C is the affine line or the projective line, what do you think are these functions? How many are they?
Is this corollary saying every divisor is principal?
Yeah, so since you know divisors, it's easy to get confused. But the others don't, so they will be fine. It's not saying that. No, we haven't defined divisor. So in case you already know divisor, you may confuse this with saying that maybe I should make a note here. So here is the warning for the experts. Well, also for the non-experts actually. I will formulate it in the following way. This f that you have, it may have other poles and zeros outside S. So zeros of f and zeros of 1 over f may actually be strictly bigger than S. Okay, this corollary is not saying that the zeros and the poles are just S. There potentially could be points which are outside what you were given in the input, which is S. Yeah, so that actually gives you a lot of extra leeway, because there are still these unknown points which can be zeros or poles. You don't have to worry about them. Those are kind of don't care zeros and poles. Important ones are only these S, and for that there is a match. Yeah, that's one thing. And second is, you can work out the set of F's in the case of projective line. Just to get an understanding of how these F's look like. The proof I have given is actually very tricky. You don't immediately understand what this F is, but if you work it out for the projective line, essentially what happens is, if you say that 1 has to be a 0, then you look at the function x minus 1, right? And if you say that 2 has to be a pole, then you look at the function 1 over x minus 2. So those kind of things suffice. They give you complete understanding over the projective line. Obviously, over a curve, it can be trickier, because 1 over x minus 2 may I mean, in the case of an actual curve, you will have two coordinates x and y. So you cannot simply do 1 over x minus 2. You have to think about what is the point x comma y. And then for a point which has two coordinates, you have to define an f which satisfies these conditions. So that will be trickier. So I think, yeah, you can easily work out the case of projective line. Take C to be the projective line and find F's. That will be a good example to understand this proof and the corollary. So let me move to the next topic, which will be the like the cornerstone of whatever happens in arithmetic geometry, which is the divisor class. Before that, I have to correct some things I said last time. Yeah, last time I was talking about the degree definition of a point. What is degree, right? That I have to correct. So maybe you can correct in your notes. The base field small k, we would now like to think of it as a finite field. It may not be fp bar. It may just be some fq. So in that case, what is a point? And a point will always be a DVR for us. Okay, we will not think in terms of point as x comma y. We will actually think of it in terms of DVR. So you have to ask the question, what is the DVR, or what are the DVRs of this function field k? In the algebraically closed case, DVRs actually correspond to an actual point. In the finite field case, DVRs will actually correspond to irreducible polynomials. So it will not be an actual root, it will be a root with all its conjugates. Okay, so for example, if you don't have square root 2 available, then point cannot be square root 2, then point will be actually square root 2 and minus square root 2. Right, so they will be clubbed together, so your polynomial will be x square minus 2. Okay, this we had seen also when we classified the valuations of the affine line. There we saw that the valuations come from irreducible polynomials. So it's the same thing. Now we are just making it more explicit, and we'll measure this, how many conjugates are there. So, but think of a point always as a DVR. It's always a valuation for us, a DVR, and hence the stalk. That's what a point is. It's a cluster of conjugates, and how many conjugates, that is measured by degree of the point P. Okay, so D of P is just the number of conjugates in that cluster. Is that clear? So I'm just correcting what I said last time. Yeah, so example is like an FQ square finite field. What may happen is that you have a point P which is square root of alpha coming from x1 equal to square root of alpha. It's not present in the base field FQ, it's present in FQ square. So the point P that you will be looking at, it cannot have square root alpha. So what it will actually have is, it will be given via this irreducible polynomial x1 square minus alpha, that prime ideal. So when you look at OCP mod MP, you will actually go to an extension. From FQ you will go to FQ square. So we will say degrees 2. Is that clear? This was always 1 in the algebraically closed case. The degree was always 1 because you actually got a real point. Now you will generally not get that. So you have to talk about degree because you are representing it. Like you can also think of computation about this. So you will actually represent the point via an irreducible. So how much do you have to store? So that storage space is given by degree. Okay, it's not an actual point, but this irreducible. The bigger the irreducible is, the bigger the degree is, bigger your storage is. So yeah, just remember this part. If you have any questions, you can ask. So for the rest of the course, the goal is to study the set of all functions from the approximation that appear in the approximation theorem, the U's. Only for curves, of course. So in transcendence degree 1 function field, what are the functions whose zeros are at least that in the set S. Zeros and poles come from this set S with specified multiplicity. Okay, so we want to look at the set of all those functions. It should be easy for you to see that the set of those functions is a vector space, because if f1 and f2, their zeros come from S with the specified multiplicity, then f1 plus f2 also satisfies that condition. So you can add these functions, so you actually get a vector space. Vector space is obviously infinite in size. Yeah, it will always, may not always be infinite, but usually it will be infinite. So we definitely don't want to talk about size, we want to talk about dimension. Why is the dimension finite? I am not sure about that, that we'll see. Yeah, so the formal construct for this is the divisor class or divisor group. Okay, so this will be divisors of a curve. Maybe I start next. So we'll now focus on divisors, which is unfortunately seems to be an overused concept. I mean, you have divisors of integers, but as we develop the theory, you will see that it's exactly mirroring that. Just like integers have divisors, function fields also have a concept similar to that, which we'll again use the term divisor for it. Yeah, but it may be too early right now to get into that comparison. Let us just develop the algebra for now. So it is the free abelian group generated by the points, which is the DVRs. Okay, this is called the group of divisors. Of a smooth projective curve which we have seen is every transcendence degree 1 function field, right. So any transcendence degree 1 function field, respectively smooth projective or equivalently smooth projective curves, you can look at the DVRs or respectively the points and just take a linear combination of the points in a formal way. Okay, so for now there is no relationship. So if the points are P1, P2, you can just look at 2 P1 plus 3 P2 or P1 minus P2 and so on. These are all just formal objects living in this free abelian group.
So in particular, the points we interpreted as coming from the algebraic closure.
The points? No. I just gave a whole prelude to that. The points are, if you have a problem with algebraic closure, just work with DVRs. P is just a DVR. So equivalently,
The equivalence between DVRs and points is only over the algebraic closure.
no. By P in C,
Function is over closed points.
P in C we mean DVR.
Means DVR. But all points are closed.
Oh,
In a variety. Yeah, all points are closed. In more simple.
no. I just, so in my notation, the big P is a DVR. You think of, so you can remove the geometry completely. Don't work with smooth projective curve. Just work with the function some transcendence degree 1 field K. Go over the DVRs, or if it is a curve, then go over the stalks.
So this is in one-to-one correspondence with points over the algebraic closure.
Over the algebraic closure, definitely, that is what we have proven. But over finite field, I have gone fast, and I don't want to get into those details. What exactly is the correspondence? But I hinted that the correspondence is essentially by irreducible polynomials. So to think of a DVR, let's say where you are in a finite field, to think of a DVR, you have to think about not just an actual point, but the cluster of its conjugates. So it's actually a cloud. It is a cloud of the point with its conjugates. That is what a point is. It's a cloud. If you really want to think about the point, but it's actually, we'll just go with DVRs. Because what we want is the valuation and all that. We want to talk about degree of the point. So in this case, you have to remember that degree of P may not be equal to 1.
What do you mean by a free abelian, bro?
Oh, free is just take all possible combinations. You are not, there is no relationship. So it's not that P1 and P2 are equal, or 2P1 is equal to 3P2. There is no relationship. These are all, just think of P1, P2 as symbols. So you have, you can take any combination, they are all, independent.
So operation is plus, right? T plus P is 2P. So those kind of operation. That is the operation here.
Yeah, so you go over the points in the curve or the DVRs in the function field, and you are allowed to take any combination. The only way two combinations will be equal if they are equal for every coordinate. That's the only content here, that
What is the operation in this group?
addition.
Addition.
It's an abelian group, it's the addition. Yeah.
So T plus P is 2P, that kind.
Yeah, exactly. Yeah. So for example, so P1 plus P2 and P2 minus P1 plus P3. So this will be 2P2 plus P3. Fine. Yeah, and of course, what is P1 minus P1? Yeah, so there is also a 0 in this group, but this 0 is not any point. It will not correspond to any point. It's a formal object in the group. Point is just P1, but if you subtract P1 with itself, you get basically empty. So it's the empty point.
So taking this cluster of conjugates, what is the use of that?
What is the use? There is a valuation, and there is a degree, and this degree is related to the Frobenius action. So it will count everything correctly when we reach zeta functions, which will be next month. So we want to keep a count of how many points are there in a finite field. So for that count, you need the degree to be working well with divisors. Otherwise, the same conjugates, if you separate them, then you have to keep track of them across summations in the divisor group. I don't want to do that.
So when you say irreducible polynomial, is it that you are intersecting that with the curve, and then the cluster of points you get is the product of, is the result of?
Correct, yeah. Yeah, I again hinted that in that example, the square root alpha example. So look at the orange example. So base field is small k is fq. You took a point which is essentially point like square root of alpha. Square root of alpha is not in the base field, it's in the bigger field fq square. So when you will look at kp, the residue field of that point, residue field will actually come out to be fq square. And the point that we are talking about, the DVR is basically given by the prime ideal x1 square minus alpha, because the prime ideal has a base representation, but the roots don't have a base representation. Roots have a representation in the residue field. So we keep a count of the storage space for us, because we will say in computers we will only store x1 square minus alpha. We can't store square root of alpha. It doesn't exist in FQ. So we keep a track of the degree. dp is 2. Yeah, and all this pain is being taken to keep the counting of points in the finite field correct on the curve, because Riemann zeta function is supposed to count it exactly. We don't want to go into approximation, so we want to keep track of that exactly. So I mean, as you can imagine, we cannot keep working with the algebraic closure, because ultimately we are interested in finite fields. So, at some point there has to be a bridge built between finite fields and infinite fields. So, this is the point. This is the divisor group that we are defining for any finite field, including also algebraic closure. Okay. Yeah. So, the other thing is, yeah, I think this is the notation here is a bit bad. The notation seems to suggest that you can take infinitely many points, but when I say sigma, I mean the support is finite. Uh, have finite support by definition. I am not deducing this. Okay, so you should think of sigma as just summing up finitely many points. For all the other points, it is understood that the coefficient is 0. Okay, the non-zero integral coefficients will appear only finitely many times, because I mean we don't have yet a way of summing up infinitely many things. Right, these are discrete points. So, you can't do an infinite sum, it is only a finite sum. So, that is already inbuilt in the definition. So, which also means that this sigma pi I greater than equal to 1 is not allowed. Okay, these kind of sums will not be allowed because this is infinite support. Okay, continuing with the definition, any element in diff C is a divisor of K. Yeah, so I mean if you want to really set up an association with integers, the integer ring that you studied in school, you should think of diff C as the integers for your curve, and any element in diff C is called a divisor. In fact, diff C you should think of as a set of divisors of the curve. And the points pi's you should think of as prime numbers. Okay, so divisor is nothing but a product of primes. Okay, so what was in school product of primes, here it's actually a sum of primes. Okay, so there is this philosophical shift from looking at products of numbers to sum of primes. That is why this comparison could be confusing in the beginning.
Just take logs.
Yeah, so you did log in class 10th. So with product of primes and log, now you have divisors.
Who defined this structure first?
Yeah, I credit for everything Whale, but I am not sure. I think the most impactful results I think are due to Whale, because this is, remember, we are doing this for any curve. General curves were not studied before Whale over finite fields. Yeah, but I think Hassa must have also developed something which Whale generalized to curves. Yeah, needless to say, these things people had done for complex curves. Like Riemann proved things only for complex curves. So we will be giving Riemann's proof for the divisor group after the mid-sem. That was for complex, but then Whale generalizes it to any field. we can now immediately define the order map. So, order at a point of a divisor should do what? So, it should send a divisor to the number AP such that D is AP times P. Okay, so the coefficients, we will call them orders of the respective point or prime.
2p plus 3q, the order is 5.
No, for a point. This order is for a point. So, for P1 it is 2 and for P2 it is 3. 5 is what you are calling 5 will be the degree. We will define that. I mean, obviously order is a group homomorphism. It is a group with respect to addition, group homomorphism with respect to addition. Right, div C is is an additive group, and integers obviously here an additive group. So, this is just a group homomorphism. Sums go to sums, and we can also similarly define degree. So, degree is slightly more complicated than you would think. So, this will be, you would think it is sigma AP, but what it should be?
Times the degree of the extent.
Exactly. The degree that we have defined for a point before. Okay, so for a divisor, sigma AP times P, degree is basically sigma AP, but you have to weigh on the degree of the point itself as well. Yeah, because the point, as I said, it's actually not a real point, it's a cloud of conjugates. So, how big the cloud is, but you have to put that weight there because you want to keep track of the count of finite field points properly. So, that is the motivation. Of course, you may not be able to see that immediately, but there is some intuition for this. This is also a group homomorphism. Is that clear? So, when you add two divisors, if you are looking at the same point in D1 and D2, then the degrees will be equal. So, A of P1 and A of P1 and A prime of P1 you can simply add, right? And if the points in D1 and D2 that you are looking at are different, then they will contribute in different places. So, this again is a group homomorphism almost trivially with respect to addition. Its kernel is an important object. So, kernel of D is called the group of divisors of degree 0. I mean, obviously they are degree 0, and they form an additive group again. So those elements are called degree 0 divisors. For example, it could be P1 minus P2 if P1 and P2 are of equal degree, or if they were actual points, then their degree is just 1. So in that case, P1 minus P2 is a degree 0 divisor. And this has a special respect that we give. It's denoted by div 0c. Okay, most of that, almost all the time we will be actually working with this div 0. Yeah, there are other small things we have to define. Let's do that on Friday. Any questions? Actually, let me continue and define two things. There are a lot of keywords. So support of D, this I kind of already mentioned. It's the points that actually appear. Okay, whose order is actually, which are actually appearing in the divisor D. That's the support set. So D will be called integral or positive or effective, depending on the literature that you use. If for all the points on the curve, the order is what? Non-negative. Okay, so the integral divisors, I mean, again you can think of integers, right? So integers which have prime factors with exponents non-negative, they are called integers. So similarly, integral divisors, positive or effective, you can define. Based on this, you can define when does a divisor divides another divisor. So D1 divides D2 just like numbers if D2 minus D1 is greater than or equal to 0. That's our notation here. So we say that a divisor D is greater than or equal to 0 if and only if it's integral or positive or effective. And we say that D1 divides D2 if the difference is that, which in other words, every order that you see in D2 is at least that in D1. Then you can define divisibility like this. And unsurprisingly, this can be written as D2 greater than D1 or D1 less than or equal to D2. Right? There is no, this is well defined. So we can remember we are defining these inequalities now in our own way. Right? We are comparing these formal sums. It's not automatically defined. Oh, and what happens if D1 is less than or equal to D2 and D2 is greater than less than or equal to D1? If D1 divides C2 and D2 divides C1, then what happens? Yeah, then they are equal, right? So this is not a stupid notation. It actually follows what you think it should. Okay, I think, yeah, this maybe we can continue next time.